button. As far as administrative stuff goes, I pushed back assignment 7 one more day, so let's do tomorrow night now. I mentioned very quickly at the end of the class, but just in case anybody missed it, last time the extra credit assignment is up. There's not a video yet. I'm hoping to get that out this weekend, but there is a video, or sorry, the rubric and the skeleton code's out for that, and it's due next month. And then next class on Tuesday, if you remember, is the exam. So today we were supposed to do a review, but we ended up doing it last time. So that's normal class time. Should be up sometime soon, as was the case with last exam. The time limit will probably be over the actual class time, just so you have some time to like finish copying and pasting anything if you're using an IDE or something. And the time window will be a little bit bigger. And then on Thursday we have a holiday, so no class then either. So no class until next Tuesday, so two Tuesdays from now, on the 16th, I think. So we got quite a while before the next class, and I guess in the meantime, again, we're done with all the syllabus stuff, so we'll definitely do a review before the final again over all the content that we've done. And then while we're just kind of having some free time, I figured we would talk about some other computer science or programming related topics. So I have a list here if you want to take some time to read over it and decide if there's one in particular that you want to look at. I should actually probably open the chat. I forgot to open that. But before we do any topics like that, I want to make sure that we take a little bit more time to review if anybody needs it. So first things first, are there any specific topics or questions that anybody had that they wanted to do more review on? Okay, friend functions? Yeah, we can talk about friend functions a little bit. So friend function is basically just, it's a C++ feature that allows you to kind of get around the fact that things are private and allow exceptions to the private rule. So for instance, if I wrote a function void print that took some class that I've written called ex, and we'll just say it has a parameter called e, and then the purpose of this is to just print all of the members of e, so maybe it prints e.name, and then after that, there'd probably be an inline, but that's okay. E dot, ID, something like that. Then we have this static function. It's global and it's written in exactly the same way that you would write one in CS135. If we have a function like this that we specifically want to be an exception to private members, then what we have to do is just let the EX class know that it's allowed to access these things. So what I'm assuming here in this case is that we've written this code and that the EX class has a private member called name and a private member called ID. And what we want to do is be able to access those despite the fact that they're private and not have it generate a compiler error. So the way we do that is we just write the class declaration as we normally would. EX, so I assume that I've written all the private members there. And then I don't think the accessor label actually matters, but I'll just put it under public anyways. All you do is you write the word friend as a way to let this class know that it has a friend, and then you give the name of the friend function. So here the name of the friend function is void print. I'll go onto a new line because I'm running out of space here, but EX. And since it's kind of like a declaration, I don't need to put the variable name, I just need to put the type. So it's basically like a variable, or sorry, a function declaration or a prototype that you provide, but it's just a marking to say, hey, there's a function that exists somewhere. It's not a class member, but what I want it to do is be able to access private variables. And so now when this function exists, assuming that you've written it, which you kind of have to, then it's going to go and say, all right, I know normally nobody's allowed to access name or ID because those are private, but you're my friend, so you can go and do it. And that's all a friend function is. And just by putting this here, you are saying that that's like an exception to the rule of privacy. And it's like a C++ exclusive thing. And where this came into play for us was in operator overloading, because we usually don't write a function called print, I guess, just for convenience. You would write in C++ an overload of this operator, just so that's a little bit nicer to read, I guess, with the rest of the C++ syntax. And so things like that operator and this one, the extraction and the insertion operators, we generally mark as friends because they're going to have to be static regardless, which we talked about last time, that these two operators cannot be non-static. They can't be instance members. There's no way that that works out because the first argument is always the stream, and then the second argument is the thing that you're either reading or writing to. And then it's convenient to make those friends. Now, you don't have to make them friends, but I would rather write this, e.name, e.id, than have to go and write, if this class had 4 members rather than just the 2, 4 getters, so like 4 get name, get ID, get variable 3, get variable 4, etc., right? Kind of annoying. So it's just a convenience thing if you don't want to have to obey by those private rules. It's just a quick way around it. Especially, I guess, to add on to that, if you only ever need to get these things in this one specific context, which is printing, and then they need to be private all the rest of the time, then it's a better idea to use a friend function than to write getters, because then you're leaving yourself open for more people to get things that are just needed in this one specific scenario, which is printing. Does that make sense? Or any other questions? For sure, no problem. Did anybody else have any other topics or questions that they wanted to cover? Okay, for sure. I don't think I see any questions. I'll wait like another second or two. Okay, I guess if nobody has any specific questions or topics that you want to go into more detail, I guess we can do kind of an extra topic for the rest of the class. So these are the 3 that I had. I did have one student suggest something, so I put both of those on here, and then I do have a follow-up for that time complexity that we talked about. So does anybody have any preference on what you want to talk about? We can either talk about more algorithms outside of the ones that we've covered in class, and then their time complexities and how that relates to other time complexities, like bubble sort time complexity. We can talk about machine learning basics, and specifically neural nets, I guess, is a machine learning model. Or we could talk about any kind of software development, mobile, desktop, game development. I might have to do some updates for some of these software on these ones. So if you guys are interested in this one, it would probably have to be after the exam, if anything, just so that we have more time to talk about it. And I give everybody else a chance to like install the software that would be necessary if you wanted to follow along, since it is just kind of like a fun lecture. So any specific votes that anybody has? And we might just do all of them eventually anyways, just because we do have, I think, like 4 or 5 open classes before we would do review. Okay, so that's one for machine learning, for sure. Mobile development? Okay. I'll specifically mark mobile. Does anybody else have any preferences? Okay. I don't see any other responses, but I guess what we'll do then is we'll probably talk about machine learning today, just because it's kind of one each. We can talk about machine learning today, and then I suppose we'll do some mobile development next week, or is 2 weeks from now when we actually have more time. That way, everybody has time to download the software. So for mobile development, there's kind of like two paths we could take. We could do it with something that's kind of specialized for specifically mobile development, like Xamarin. And so this is like a cross-platform. I guess just to mention in advance, no matter what we do with this, it is not going to be in C++, just because mobile development is not done in that. So we could do something with Xamarin, which is in C#, and it is like for iOS and Android, as well as UWP, which is Windows applications, iOS, Android. And this isn't intended for like specifically mobile. So it's kind of catered better to it than other platforms. And then the other suggestion I have would be something like Unity, which would also be game development. So we could do Unity, which supports mobile exporting and would specifically be for games. You wouldn't usually want to do this if your target is iOS and Android and you're trying to make like a traditional app. But this also supports iOS and Android. And it would also be in C#. So just to get a feel of what we could do. So does anybody have a preference? Would you rather do something that's like strictly mobile related or something that's game and mobile related? Okay, Unity, that's fair. And honestly, if we have time, we can probably do both too. But I guess just as a starting point. Okay, so I see 2 for Unity. Fair enough. We can do Unity. So I guess we'll do that after the exam. We'll talk about some Unity stuff. Just in advance, try to have it installed so that we can talk about it. You'll want to have Visual Studio installed if you're doing it, especially if you're on Windows, and then Unity itself. So you can download Unity Hub, and then the most recent version is something like 3.20 or something. Okay, so we'll talk about that stuff next week then, and then maybe we'll talk about Xamarin if we have extra time. But I guess today we'll talk about machine learning and neural nets. I don't have lecture notes for this, so I guess I'm going to kind of just freestyle a little bit, but I do have a general idea of what to talk about. So let's at least address some intuition into machine learning in general, first off. So let's say you have a data set, right, that looks something like this. So you've probably done some examples of this in maybe your high school math, something like this, where you have a collection of points. And what we want to do is we want to make it so that if we were to add more points to this, we could have a good idea of where they would fall. So for instance, let's just say that this is flowers, so we'll just go with the iris setosa example. It's a common data set that tries to do predictions of flowers. Actually, I guess that's probably not a good one because it's a classification problem. Let's say, we'll just go with the classical example. This x-axis here represents the age of a child, let's just say of people ages 1 through 18, and then this here is their height. And so assuming that there's some sort of correlation between these, which we can kind of assume there is, it looks like there's almost a correlation between these, then what we want to do is come up with some sort of model or function that allows us to make a prediction about our output y in terms of our input x. So I think the most obvious way to do this, if we were just going for the simplest solution, is just let's draw a straight line, and then that is going to be our predictor. Right, so we get all these people, we figure out that this is their age, and then this is their height, and it seems to fluctuate like that. These are all just like separate individuals, and it seems like there's a positive correlation between age and height. And what we want to do is, given somebody's age, maybe we want to predict what we think their height is going to be. And so, if somebody was 2, and then this is 6, and then maybe this is like 10, then if I was to say somebody is 7 years old, and I want to figure out what their height is, then we would expect it to be on the line right there, right? So this line is a prediction of what the height of somebody is going to be based off their age. So the way we generally represent things like this is with y hat. So y hat represents a prediction, which in this case is a scalar. It's just one single number. It's a height, but it could be a vector. We'll see in more complicated examples. And here, what we did for our predictor, our y hat, is we just drew a straight line. We said, okay, well, if I was to try to make some sort of correlation, this line is probably simple enough, and that's fine. And so we can represent this with something like mx plus b, right? And so this is how we find it. And the goal of this, right, is that we find some m and b that form this line, and then we can plug x into it and get our prediction y hat out. So here, maybe this prediction is something like the slope of, I don't know, this is 7, let's say this is like 40 inches or something like that. I have no idea how tall children are, so that might be horribly wrong, but we'll just roll with it. This seems to be like up 40 over 7, let's say, so maybe we find out the slope is 40 over 7 for the line we drew, x plus something like 0.1, it's something really small. And we could make other predictions, right? We could do other lines where I could draw another one like this that maybe has a lower slope but a higher y-intercept, and it's maybe slightly better in some cases and slightly worse in others. But generally, we want to make something that's good at predicting the data. So that's kind of our goal here as far as machine learning goes. It's going to be more complicated than this, but we want to make some sort of prediction given some sort of input data. Right? So maybe if we were to make this more complicated, we would maybe want to do a height prediction, not just off of age. Maybe there's still more factors that contribute to the height, like maybe weight has a correlation with it. I guess you could say like birth sex, something like that. And we could have like this list of factors that we think contribute to the height or may have some correlation with it. And so this x here, even though I'm representing it as just like the age in this example, it could be a vector. And it could represent all of these things at once. So just don't get confused here. X doesn't necessarily mean like the traditional single value x. It could mean something like this, where it's a collection of numbers. And if we have something like this where there might be categories, then we might do it with some sort of enumeration, or try to do something better depending on the context. So we might expect a vector like this to be our input, and we can make some sort of output for it. Now we can't represent this with a 2D graph, but we could represent something like this if we just threw out this one. Said age and weight, we could do something like that with a 3D graph. So just for the sake of understanding the concept, let's go ahead and draw that out. So just as far as the intuition goes, let's say that my input vector, and I'm actually going to rename this in a second, we'll do it that way. My input vector is 2-dimensional, and it takes in two things, being the age of the child and the weight of the child, and then we want to make some sort of prediction here on the y-axis about their height. I'm actually just going to represent this as x0, x1. So I'm going to use this notation from now on, where the components of our input x are going to be subscripted. So the first one will just be 0 and 1, kind of like how you would index an array. So rather than x and z axis, even though that's how you normally think about it in a math class, I'm going to call this the x0 axis and the x1 axis. And then y is going to be our height axis. So you can see here, anything that falls on this vertical axis is going to be our height. and anything that falls over here is going to correspond to our weight. So we have like a weight axis, we have a height axis. All of the things that go in this direction have to do with height, and then anything that goes in this direction, like in and out of the screen, has to do with age. And then we may have some sort of positive correlation here. It's a little hard to draw, but we'll say that these are like kind of going towards the screen, right? Like this. Now this becomes a little more complicated. We can't necessarily just do this with a line anymore. We're going to have to do this with a 2D manifold. So kind of like a plane, but imagine if you took a piece of paper and it just like curved around in 3D space, like this, right? Something like that. And then we have folds on it. So rather than a line now for our predictor, we're going to have to do something more complicated. And we don't need to concern ourselves too much with visualizing that, but just consider that that's where some of our intuition is going to come from, is like putting that a kind of curvy piece of paper into 3D space. And so we have multiple different approaches to this, right? So we could do this in much the same way that we did in 2 dimensions, where we say, okay, well let's just do it as mx plus b, where m is the slope, b is the y-intercept, and then we just let x be a 2-dimensional vector now. So when we actually multiply it, we multiply the slope out by both x0 and x1. So that's fine. You could have like a plane in that case, that'd be okay. But sometimes it's not the best case for doing our data. So here I would propose maybe something that's curvy would be kind of good. Let's go back to 2D just to make this a little easier. Let's say I have another data set. It's kind of like this. So it's no problem for me to do something like that where I just do a straight line, but it's probably not good to represent my data. There's probably a better way to do this, and maybe one way to do that is with a cubic function, right? I do something like this, and now all the points are a little bit closer to our actual line. So we could represent this as something like ax cubed plus bx squared plus cx plus d, where a, b, and c are just some numbers. They could be positive or negative. They're just like floating point numbers. And we can find that and just find something that works pretty well. But I guess my point here and why we're doing this is you don't always have to represent things with a line of best fit, like a linear regression. You can do things that are kind of curvy, and you'll see in a case like this, it kind of does a better job than if we were to just draw a straight line. Now, one thing to be careful of is that you don't go too crazy with this, right? I'm doing a cubic here, and it's fine. It goes through the data pretty well. It seems like there's kind of a balanced amount on top and bottom. It seems to go through them pretty decently. I could also do something like this, right? That perfectly goes through all of the data, and it's like a high degree. In this case, it would be 1, 2, 3, 4, 5, x to the 5th power, and then have all those coefficients. And it's a good idea not to do this. So if you go too overboard, that's called overfitting. And what that essentially means is that we have gone and tried to go too close to the data, and when we make a prediction, it's going to be bad. So consider if I had something like this, because of the way that it's drawn, if I go to make a prediction at, like, let's just say this point where x equals something like 7, then my prediction is going to fall on my graph. That's always the case. And you'll see there's a kind of match up, this blue one and this green one here. Let's say I actually move it a little bit further over for the sake of our example. We try to make a prediction right here where x is equal to 7.5 or something, is that we get a prediction that's kind of nonsensical or is like too hyper-tuned to the data. So here this ends up like way far away and is much a worse prediction than a simpler model, which was our like cubic one. So don't go too overboard. Don't try to make anything too complicated. You want it to basically represent the data as well as it needs to, and no more precise than that. So at least this is making sense so far, that we don't have to necessarily do it in the way that you may have done in high school, where you do a linear regression. You don't always have to represent the data with a line. We can do something more complicated than that. At least as an intuition. Yeah, okay, fair enough. So then what I'm going to propose then is that we try to do this with a neural network. So a neural network is a new, relatively new, I think it's probably like 40 years old, but it gained popularity recently just because computers have been getting faster and we've discovered good ways to do this, where we can create a complicated function that will model the data. And in these cases, we're going to just say that x is going to be our input. So it's some sort of input vector, kind of like what we had before, where it's just going to be a collection of our features that we want to try and make a prediction about. And then we're going to have y hat, which is going to be some sort of output vector, which represents what we think the result is. And there's multiple ways that we can frame this. We can frame this either as a classification or as a regression like we did before, and I'll try to explain the difference between those. And then we're going to have another y, which is our truth value, which is also a vector. So pretty much all the things that we're going to deal with are going to be vectors. So let's say I go back and I do that, that one example again, where we have something we want to make some sort of prediction about. We'll do a regression in this case. And we'll say that as the input vector, we're going to take in the age and the weight. And then in this case, our output is a scalar. Even though I said it's normally a vector, we're going to just say it's a scalar, and it's a single thing that represents, in this case, just the height of the person. So let's say I have this data, 1, 2. Okay, so it's not realistic too. It's probably kind of bad for a weight. I will say 20 pounds for, say like 28 to 36. We'll just deal with these ones, and then we have their heights. So something like, I don't know, maybe these are in inches, so 24, 27, 26. We want to come up with some sort of complicated function that is able to do a prediction on these. So the intuition behind machine learning is that we use some data that we know about to try and make the computer figure out a function that it can use to make this prediction. So I guess in the previous examples, we were just kind of looking at it from an outsider point of view where we have access to this data. But I guess my point in trying to draw things like this in 3D and kind of demonstrate it was some of these can become so complicated that, you know, obviously you can't just look at it and make an honest prediction, right? Like let's say you have 200 inputs, then it's a lot harder than something like this, right? You are in 199, actually, sorry, if you have 200 inputs, you're in 201 dimensional space, and like that's, nobody's visualizing that, you're not going to be able to make a prediction. So what we want to do is be able to train the computer to figure out what those coefficients are and biases are so that they can do a better job making a prediction than we can. And so the way it does that is it takes some sort of historical data, some data that we know. In this case, that's what we're going to do. At least this is labels, is what we call this, where we know the inputs and we also know the outputs. And when we do it this way, this is called supervised learning, where we know what our target is. We know some examples of things that are in our actual like data set, and we know what their output should be. It's supervised. And what we're going to try to do here is we're going to try to train a model, basically a function, and tell it what coefficients it needs in order for these predictions to be pretty close and model something like what we had with those ones that we drew by hand. Okay? So the way a neural network works specifically is that you have nodes. And you're going to notice this a lot if you're a computer science major, is that a lot of a lot of algorithms are going to use nodes, and the way you would implement these is not like the nodes that we've talked about in this class, but just bear with me, they're also called nodes. And specifically neurodes, I guess you would call these. These are called neurodes. And this right here is going to represent our input x. So these are our starting point. This one is going to be x0, and this node is going to be x1. So we just kind of line them up vertically, and we make a network, which, if you're familiar with discrete math, is just when we kind of link these things forward. So we have our input here. Essentially, as we propagate forward in our neural network, what we're just going to do is we're going to take each pair of numbers that we have, or all the numbers in our vector, and just kind of plug them in to this specific, to each node. So if I was to plug in this vector here, I would say that the 1 goes to this node and the 20 goes to that node. And then if I was to plug in this one, the 4 goes to that node and 28 goes to that one. So they go in groups. That's kind of what a vector is. And then we apply them into some number of hidden layers. For the sake of my example, I'm just going to do 1. I'm going to keep it simple. So I'm going to do 1 hidden layer here. Let's do it like that. And what these are going to do is they're going to receive inputs from the other nodes and then try to make some sort of prediction. So what they're going to do is I'm going to output whatever I get from this node, whatever number. I'm going to multiply it by some number. I'm going to say W, 0, 0. I'm going to call this node H, 0, 0, and I'm going to call this one H0, 1. And the names I'm coming up with these are, this is W for weights, which represents the coefficients that we're multiplying by. They're called weights when we do a context like this. And the H here is probably not common notation or anything. It's just, I think it makes sense here. The first number I'm going to say is the number of hidden layer we're on, because we could have multiple. And then the second number is like where it is in our layer. So this is the 0th node and this is the first node, if that makes sense. And then as far as my weight notation, I'm just drawing this as the left number will be the number it's going from, so the node it's going from, and then the right number is the one that is receiving on the other side. So this is going from node 0 in our input to node 1 in our hidden layer. And I'm going to do the same thing. So I'm going to fully connect this, is what this is called, where everything is connected. And what each of these connections is going to represent is just a number. So I kind of said it earlier, but these are just going to represent coefficients. They're going to be some numbers that we train over time to make our model better. So if we go for one of our simpler examples here, that would kind of be like this A, B, and C, and D that we had. Or in our linear example, it would be like the M and the B. The goal of making something like a linear regression is that you find a slope and a y-intercept that are able to go through the array correctly, right? Or sorry, the data set correctly. So those are the things that we actually need to change and update and figure out what they are. The y hat is our prediction, and the x is our input. So those are the things that we can't change because we can't, just fudge our data or anything, right? What we need to change is the way the function looks, the form of the function. So that's what these are going to represent. As far as this goes, let's go ahead and write it out a little bit further. The way that you apply these connections, these feed-forward connections, is that you multiply by these numbers. So what's going to be received by this node here, this guy, is going to be x0. So I'll represent x0 in red and x1 in blue. This is going to be x0 times the weight that it needed to go to get here, which is w00, plus x1 w10. So the way we get a value for this specific node, at least just to start off with, is we're going to take all the nodes that came before it, multiply it by some value, and then add all of the inputs that we're getting. Is that clear so far how my connections are working and how we're getting to this specific node? Okay, fair enough. And if you have any questions at any point, stop me, because this is going to be some complicated math probably at some point. So totally understandable if you have questions. So that represents our input to this node. I guess for the sake of this, I'm going to call this A0. I'm going to call that, actually, sorry, D0. Again, everybody has like different notation and letters for these, so take mine with a grain of salt. I usually call these dendrites and axons so that it sounds like a brain cell. I just think it sounds cool, but normally maybe people will say like pre-activation and post-activation, but then P doesn't work too well for a letter, so I don't know. That's just what I'm doing. So our D0 is going to be all of the things fed into it times the weights that they had to travel to get there. And then what we do when we actually do these in practice is we add something extra here. I want to make it clear that that's not what I'm pointing to, but we added a linear, or sorry, like a constant to this. And the B is a bias, is what that's called. So it's kind of like our mx plus b in the context of our linear equations. It's just an extra number that, if you notice, is not affected by any sort of variable. So it's not multiplied by any sort of node from previous layer. It's just kind of free floating and hanging on to this node, and it just adds to it. And we are still going to update this as part of our actual solution. But it's not going to be affected by the actual input data. Okay, so that's our general strategy. Let's go ahead and try to do this one together. So let's say I go to calculate this D1 here, this dendrite value for the bottom layer. Can you guys try to figure out what that would be, or make a guess? So what's going to be my component coming from this node? Zero, 1. So I assume you mean the weight part. Yeah, so that's going to be the weight that it travels, and then that part is going to be specifically the path traveled by x0, right? So is that part okay? So it's the thing coming out of the last node times the path that it's taking to travel. What about the next part? So if we take this node and travel to the input at D1, right, x1, yeah, you got it. So x1, and then that travels the w11 path, which we multiplied by. Okay, so looks good. And then the last part is we want to, yeah, right, you got it. Add the B1, the bias to it. Oh, okay, so good job, guys. That looks good. So this is going to be our input to this specific node. And so every time we do a layer in a neural network, at least a standard neural network like this one, we're just going to go ahead and do that process. And it's going to be shared across almost all neural networks. We're going to have this same kind of idea where we multiply by it. More commonly, just as a side note, you'll maybe see this more often written in a linear algebra sense, which I'll try not to bore you too much with, but it would be something like this, where you would say w times x plus b is going to calculate my next thing. So rather than nodes, they'll usually say this is in terms of vectors. If you remember your like matrix multiplication and vector multiplication, then what this is just saying is we need to multiply this x vector here, which is x0 and x1, by all the weights in this thing. So this actual one that I drew here would be a 2x2 matrix, where this is w00, w01, w10, and w11. So in practice, we do these as matrices and vectors. And that actually makes it, I think, easier when you're programming these, but for the sake of our picture, we're going to do it as an abstraction. Right, so after we get all this input to a layer, comes the part where it becomes a little bit complicated. So far, really, all these layers are both just linear in nature, right? We have nothing that's over a power of 1. This is just x0 times w00 and x1 plus w10. Even though there's multiple variables, it is still linear because they're all just to the first power. And so we are going to have a problem if we just proceed this way, like we did earlier, where, you know, if we just do things as a straight line, it's going to be not so. I guess our problem is we want to make things more complex so that it does a better job of modeling the data, but not too complex to the point where it overfits the data. And so we at least want to introduce some non-linearity, make this not completely linear, and the way we do that is with what's called an activation function. So you can kind of see here, I've drawn a D0 and D1, and I've drawn like a middle line here. And so I'm going to have values on the other side called my axon values, or post-activation values, that are going to represent my output after this is passed through the specific node. So for every node, aside from the input and the output, what we do is we apply an activation function. And that is just some mathematical function that is, I guess I should do this in a different color, that is non-linear in nature. Generally, there's one exception to that that's common, which is ReLU, but we'll kind of skip that for now. So this is, we're going to apply an activation function. And this could be any number of functions, and you'll see that some work better than others, especially in certain applications. So if you have some sort of knowledge about your data set, you can usually do a good job picking an activation function. But common ones are hyperbolic tangent. You might do something like ReLU. You might do, why is the name? Sigmoid. Are all pretty common ones. And these are all just nonlinear functions that we can apply. So what we do to generate this activation value, I'll just do it up here on the top, is we take whatever was on the left side of our node, whatever was incoming, and we apply that activation. So here I'm just going to say sigmoid, which I'm going to do with the symbol. Normally do that with sigma of D0. I might have to look up sigmoid. I don't necessarily know if I remember it offhand. I think it's something like 1 over 1 plus e to the x power is sigmoid of x. So it's a function. It's something like this, and as far as its appearance, it looks something like that. Might have to double check on that. I think I'm right, but I could be wrong. But that's how we're going to add, kind of like pass this value across the membrane there. So we get an output there. Okay, so is everything clear so far? That's the whole process of generating any specific hidden node. You linearly find some input by applying all the nodes from the previous one, and then you apply some activation function to get your actual output for that node. All right, fair enough. And so this process basically just repeats as many times as you want. What we would do is, if we wanted another hidden layer, which I won't do, we would just feed these forward in exactly the same way, where the value coming out of these is going to be their A0, their actual axon value. Oh, whoops, sorry, I said A0 in this one, but I meant A1. And we would just keep going with this process. Now, for something like our example that we did here, I think that'd be a little bit overkill to do more than one layer. And generally speaking, the more layers you do, the longer it takes for this to propagate. So you want to also kind of keep it relatively shallow as well, and try to keep your node count down. So for the sake of something really simple like this, then this is probably more than enough. This will probably do an okay job. But at some point, you're going to want to stop doing hidden layers and finally make some sort of prediction. So for your output layer, that will be some amount of size based off of how many outputs you're going to have. In our case, our output was just one single thing, which was our height, right? This is going to output one single node. That's it, that's its output. And that's going to be our y hat that it actually outputs. And we'll have one final kind of connection here coming from all of the nodes that were in the hidden node before it. So I'm going to call this W10. Actually, I suppose this should have three 3 scripts. I'm going to call this W0. I'm just going to use the letter U. This would be another weight matrix. I should have done 3 on this one, but I was not thinking ahead. We'll say 0, 0, and U, 0, 1. But it's going to be another, or sorry, 1, 0. That's going to be kind of like this one, where it's just a matrix of weights that goes to our output. And we're going to have a unique one for each like bridge of connections that we have. Right, so this will be found in exactly the same way. It will have some sort of dendrite value. I'll just call this, I guess dy is probably not good. We'll just say d2 and then a2 here. But realistically, I would have more subscripts, but that would be, it's a bit much. So I'm going to not go too overboard. And we would apply these in the same way. So we would multiply this by a 0, multiply this by a 1, add them, and then apply the sigmoid. And then we'd also have a bias here as well. So this is our, let's call it B2. And we finally arrive at some number. So it makes some sort of prediction, and now we have a function that represents it. So I could write this whole function out. It would be kind of long because we have all these inputs and all these sigmoids and stuff like that. But hopefully it's clear that we have some sort of function with coefficients that we apply in compositions, I guess, and it finally outputs in something. And so kind of the purpose of doing a neural network as your machine learning model is that it has those compositions. We end up doing something here and then applying the nonlinearity through some sort of activation function afterwards, and then make some prediction. So that's all well and good, but as far as running this through, at least if we were to just randomly make a guess as to the values for all the weights, the W00, W10, etc., then we're probably going to get something that doesn't do a great job of making a prediction. So usually the way you do this is you make some sort of random numbers for those on some sort of scale, just keep it relatively small if anything, and then have it make an output. But by random guessing, you're probably not going to get something that does a great job of making a prediction. So then comes the problem of, well, how do we fix these? How do we make them better? And so there's a way that is considered common to do this now, which is gradient descent, which we'll talk about in a second. But I guess one thing to mention is that there's 2 parts to trying to make a prediction here, is at least if you're training. So I guess we should talk about that too. But the idea is that we do a forward propagation, which is what we did, where we make the prediction. So we start with an input, make a prediction, and then we're going to have the opposite of forward, well, not really the opposite, but kind of like the reverse of it, which is backwards propagation, which is we're going to start the output and try to like fix things and make them go. So before we do that, let's talk a little bit about training and testing. I guess I should probably go back over to the data set really quick. So this is my training data. It's really small. And I will want some kind of testing data. So there's kind of like 3 classifications for your data. There's your training, there's your testing, and then there's your real world data that you're expecting to make some prediction on. And then maybe you can use that to train as well, depending on the context. And so our process kind of goes in 2 ways. What we do is we're going to train the model. So we're going to find all of those weights that we were talking about here. We're going to try to find those numbers. And then what we usually want to do is we actually want some section of the data. So here I'm just going to split, I'm going to just put the last one, which would be horrible in real life, but it's fine here. Just maybe like 20% of your data, or so, 20 or 15%, that you use specifically to test how good your model was. And so we had that issue we were talking about earlier about overfitting. What we're going to encounter as we do this process, because we're kind of automating it, is that it's really hard to tell whether your data is completely overfit to your training data. And so what we do is just kind of divvy out a section of your data set to specifically test how good it is and make sure that you didn't go too crazy. We don't do something like we did earlier where we put too high of a degree or something, or we update things too much. So there's kind of like 2 phases that we split this into, training and testing. This is what we're talking about so far is our training test. our training section. When you're doing testing or any actual real world predictions, then you're only going to do the feed forward. You're not going to do this process that we're going to talk about now. Okay, but let's actually get into that. So we've done our feed forward. We've started with some inputs. We've gotten an output. That's great. When you are doing training, what you want to do is you want to figure out how good your prediction was. So that's kind of the goal of a lot of machine learning, is you want to make your prediction as best as possible. And so I'm just going to represent this with an eye really quick. We need to figure out how off our actual prediction was from the data. So if you remember, y hat is representative of our prediction. It's what our model thinks is the correct answer. And then the advantage of doing something with labels, with this supervised learning, is that we know what the correct answer actually is, right? So if I plug in this value over here with the 1 and the 20, and it makes a prediction of 17, then I know that the correct answer is actually supposed to be 24. And so I can use that information to try to correct how wrong I am and make it better. So what we usually have in any sort of machine learning model, neural nets including, is some sort of error function, or you'll hear it called a loss as well. It's a loss function, and it represents how wrong we were. So a really simple way of doing that is just subtract the two. It tells you how far apart they are. But we actually kind of have an issue with this, and it's specifically the fact that we might accidentally balance things off. So let's say I have a y hat, it predicts 20, and then the actual value it was supposed to be is 17, and how far apart they were was 3. But if I make another prediction later where I predict that it's 16, but we know that the actual answer was 19, then my error is -3. And so these, if we're doing things in terms of like checking how off we are, if we go to sum these up later or do any sort of statistics, then the fact that some are positive and some are negative is going to give us a bit of an issue, because they're going to cancel each other out. And so if this was something that was super off, like if this was 300 and -300, then my model is probably bad if it's that wrong on both of those things. But if I try to do some analysis on this, it's going to end up saying, okay, yeah, your model's great. These sum up to 0. Your error is basically 0. And so I'm going to try to avoid that. We're going to just not do anything that could generate a negative. So there's two ways we could think about that if we just kind of take a naive approach and we don't know what the solution is, which is we could just take the absolute value of this, right? But I know it's something in advance, so I'm going to say let's not do that. Instead, I'm going to square our value, and that will always make something positive, because if you multiply something by itself, then it's always positive. And now this solves the issue of sometimes introducing negative numbers and then doing something that would make our error seem a lot less worse than it actually is. And this specific function that I'm doing is called mean square error. I guess normally you would take the mean of all the square errors, but I'm just going to do a single square error for each individual output. And it's just going to be our distance between our two things and then square it. That's the most common loss function. Almost everybody uses it. It's really simple. It's computationally very fast. So that's what we're going to do. But we're still back to our problem, at least, of, well, we need to update all this stuff. So we need to fix all of our weights and our biases in such a way that they do a better job of making a prediction. But now we have at least a way that we can frame our problem. So if we kind of consider here, if this represents our error, then if we were to try to think this out intuitively, what's the best thing we could do with our error? What's the best value it could possibly be? If our model was completely perfect, what would our error be? Right? Yeah, you're right. 0, right? So kind of our goal here is that we want our error to be 0, which is not always realistic and not always possible without overfitting. So what we're going to do here is we're going to aim for 0, but we're going to just try to go for whatever the smallest value we can possibly go for is, or at least try to make an attempt to make it smaller. So now we're going to frame our problem. If you're familiar with game theory, this is kind of like the idea that, or like a popular idea in game theory, which is we're going to try to minimize how bad we're doing. We're going to try to minimize our loss, which is this function. Now, then comes the question, and it's going to be kind of vague, but how do we minimize loss? Can you think of anything you've done in math before that's good at minimization? Or how do you find the minimum of a function? Does anybody remember doing anything like that in math course? Limits? Okay, you're kind of on the right track. You're on the right subject at least, so calculus, definitely it. And we're going to need to use a limit. I'll give you another chance. Do you want to do something more specific? If not, that's okay. You're in the, oh yeah, there you go. You got it. So derivative, right? One of the things you can do with a derivative is you can set it equal to 0 and it will tell you local maxima or minima, right? Yeah, so good job. You're right. Our goal here is now, if we want to minimize this, we can take the derivative of our error and then try to update things in such a way that we approach the minima. Now, I'll just kind of mention offhand, I won't go into a whole lot of detail, but if you've taken calculus, which I assume everybody has, you might remember that both minima and maxima have derivatives of 0, right? Both local and that. So let me actually draw this a little bit further out. And another thing is there might be multiple minima. So there might be several points at which our function has minima at. And in the case of our problem, we probably want the absolute minima. Although we're not always going to get that. It's not always realistic, especially given how complicated our problems can be. We're not necessarily always going to find it, but we want to approach that in some way. But the other, I guess the issue is we could also, if we're just strictly trying to find the derivative in where it's equal to 0, we might hit a maxima. And that's going to be kind of the opposite of what we're trying to do with our problem, is we would maximize the error, and that's not good. Then we would be aiming for a problem where we try to make our model as wrong as possible, which is not good. But we do have a special case here. So part of the reason why we actually use this function specifically, and rather than an absolute value, which is non-differentiable at its minima, or anything else more complicated, is that this is a square, right? And what do we know about quadratic functions? If we think about quadratic functions, at least in 2D, okay, I don't know why this isn't erasing, but if we think about quadratic functions in 2D, then they're either like this, where they have a single minima and that's it, or they're like this, where they have a single maxima and that's it. So part of the reason we're using something that's quadratic in nature is that we can be guaranteed that it's going to have only minima. And so that kind of solves our problem. Now we don't have to do anything complicated with second derivatives or check the concavity or anything like that. We know that we're going to have something that is basically monotonically decreasing. Or, I'm sorry, but that if we phrase it in a certain way, it'll be monotonically decreasing. So we kind of have that advantage here by doing this square part. But now we have to actually take the derivative and figure some stuff out and update things. Right, so first things first, we need to phrase this in a way where we can figure out how to update these. Because if we think about it, just taking the derivative of this isn't going to do us much good, because that just tells us how it's changing, but we don't know how it's necessarily changing in terms of all these variables. Plus, if we try to just take a general derivative, we have like 1, 2, 3, 4, 5, 6, 7, 8, 9 variables, and that's kind of a lot of work. So we do actually have a way to do this. There's iterative ways that you can try to find a minima. The way that's usually taught in a Calculus 1 course, or Calculus AB or BC if you took that in high school, is Newton's method, which is fine, but it's not really considered commonplace for machine learning. What we actually do instead is a method called gradient descent that is very similar in the way that Newton's method works, if you remember how that works. I do think I remember it offhand, but I want to make sure that I don't make a mistake, so I'm going to double check that I have it right. And the notation, I did look it up the other day on Wikipedia, is different than the notation I'm going to use, but okay, yeah, I think I'm fine. So what we're going to do is we're essentially, for any value that we have, I guess I'll partly use their notation. For any value that we have, I'll say v of n or t or something like that. Again, these are written in a bunch of different ways. One way I can do this is I can iteratively update it by doing v of n equals v of n minus 1 minus, they have gamma, I'm going to put eta, which I could draw better. Eta, you'll sometimes see this as alpha, the Greek letter, times the derivative of the function, which it's not great, but I'm just going to put f prime of that specific value, which is v of n. And if we just kind of at least think about the intuition behind this, what this is saying is if we want to get a new value on our graph or in our function, what we can do is we can take the previous value and travel some distance using the derivative to arrive at a new point. So let's say that I have a point here, and this is my v of n minus 1. It's my first prediction. I'll actually just say v of 0. This is my first prediction, and I want to get closer to this thing. Is what I can do is I can use the derivative, which you remember is the slope of something. Okay, I guess we're just sticking with that line because it's not letting me erase it. V of 0. We can use this line as kind of a predictor of where the function is going. And by negating it, we're always going to follow it in the direction that it goes towards the bottom. So for instance here, what we might do is make some prediction here, and then go down by this much, let's say, and then reappear on the graph right above it. It's kind of what this process is saying. So that's our new prediction. This is our V1. And so if we keep doing that over and over again, where it keeps following the derivative over and over again, is that we should hopefully approach this minima, or at least get close to it. Now, eta, I haven't talked about yet, but this is our learning rate is what it's called, and it's basically just how much do we want to follow this line. So if this is a really big number, what we're going to do is just kind of follow this line a whole bunch, and it's going to jump around like a whole lot every single time. And if we keep it something small, it's just going to jump a little bit. So if I had it like as a really small number, like 0.0005, then it might slowly approach it from this direction. But if I had it as a big number like 4, then maybe it'll jump over here, and then jump over there, and then jump over there, and then jump over here. So it's kind of important that you don't pick too big of a number because it will jump around a lot. And because it's dependent on the derivative, it does factor in the slope. So you'll notice that the slope gets like lower as you get closer to an actual minima. So it tends to be more stable once you actually get close to the derivative, and really noisy and jumps all over the place when it's far away. Is that you don't want to pick it too big, because if you jump too far, you're going to just jump straight past your minima. So this is something that you usually, in practice, you try to pick and fine tune over time. The research is kind of going in a way that this in itself is also being picked by some sort of machine learning model. It picks the learning rate to do a better job. Generally, this is also constant. You want this to be consistent, like, well, the whole time you jump about the same proportion every single time. But you'll notice that some people kind of like I guess, cool down is maybe the word I want to use, where they decrease this over time. But it's basically like how far do we follow our derivative in the direction of our minima. But this process is known as gradient descent because it gradually descends towards a minima. And we're going to use this to update all of our variables in the context of our problem. And this is common in pretty much every machine learning model. It uses gradient descent, and neural nets are no different. This is generally how you do it. Right, so we have all this complicated stuff that we've put off to the side. Now we need to figure out what the derivatives of those things are. And so what we should do here is, if we want to update each one, we're going to need to find the derivative with respect to that specific variable, because if we're using that gradient descent that we mentioned, we need the derivative to be in terms of the specific value that we're updating, that v that we had earlier. That's the thing that we need to update. So v I just said generically, but that will be all of the things that are variable in the context of our model, i.e. the weights between each of the nodes and the biases between each of the nodes, or like connected to each nodes. Those are the variables that we need to update. So we can do a bunch of complicated math. We can take the derivative and do all that, but I at least want to give some intuition into like the easy way to do this, which is for your back propagation, which is the process of updating these, is to just kind of follow the arrows backwards. So let's say I want to do b. The way I'm going to do that is I'm going to start at the end and follow all of the arrows until I get up to b here. So if my goal is to find the derivative of b2, then what I'm trying to do, man, there's like no more space left. We wrote a lot of stuff. I'm gonna maybe, can I crop all this stuff over to the side? Okay, that's good. Cool. I'm just gonna throw this way over there. Or worry about it later. But let's say we want to find the error of b, its derivative. Our goal is to then find db2 te. Or excuse me, other way around. We want to find out how much the error is affected by this specific bias. And we're going to do this for every single variable that exists in our model. We want to figure out what is the derivative with respect to the error, since the error is the thing we're trying to minimize. How much does it affect our error, and how can we improve by it? And so the easy way to do this is to do it as a chain rule. So remember, I said earlier that this is an example of composition of functions, because we're just going to keep applying this activation over and over again, is that we end up having a lot of composition of functions as we move forward in our neural network. And if you remember your calculus, the way you deal with derivatives of composition is with the chain rule. We can do this in a really neat kind of like cheating way with this, which is that we can kind of like follow that path backwards. So I kind of erased it here, but we're going to start at our output and then arrive here eventually. So if we can consider what happened, well, actually, sorry, I guess we should start 1 point backwards, which is we apply the error function to this as well, and then we get some sort of error. So we're going to start at our error and work our way backwards. So the first goal is we want to take the derivative of our error function, which is this guy. So we'll take the derivative of the error with respect to its variable, which is y hat, because that's kind of like the actual thing that's dependent on our model, right, is y hat. Y is the truth value, the thing that we knew about in advance. And we can take this derivative pretty easily, right? One extra thing I want to mention, I'm going to throw 1/2 out in front of that. The reason is it will make your derivative easier. Now, I won't do the derivative for now. If you're curious, just ask me during office hours. I can always write it out for you. But for the sake of time, I'm going to ignore the derivative and just assume you know how to do that from calculus. And this would back propagate one layer. So for each of these layers, we're going to, or each of these arrows that we're back propagating, we're essentially going to take one derivative. So this is now if we take the derivative with respect to y hat, we've propagated backwards across the error. And we can keep going. So if we were to do the next one, the top is going to be y hat, and the bottom is going to be something else. And these are going to cancel each other. And that's kind of how we're going to apply this chain rule. So at this layer, we did the error, and what it took in was a y hat. So we're taking the derivative of the error with respect to y hat. We consider once we get to this point from our back propagation, we got the y hat was a direct function of this a2. In fact, it's just the same thing. So that's trivial. We're not going to do that. But we are going to, in fact, maybe I should say this is a2 instead of dy, just for clarity. So just a note that y hat and a2 are the same thing here. We've taken the derivative up to this point, the a2. What we need to do is propagate it, actually not as far as I'm saying here, but across this layer right there, which is going to be the derivative of a2 with respect to d2, right? So if we kind of consider the way we found these, right, is that we applied whatever the activation function is to d2. So a2 is a function with respect to d2, and we can see that represented in our derivative here, is that our output was a2 and our input was d2. So that's where our derivative comes from. And then the canceling trick that I mentioned earlier kind of works here, right? We can cancel those if we look at them. And then let's just finish this really quick. We would then finally do d2, whatever the derivative of d2 was with respect to b2. And these would all cancel. And you can see that it simplifies to de db2, which is the derivative of our error with respect to the bias. And in this way, we can then find the actual derivative that contributes an error from this specific variable. And I apologize, I am late on time, or short on time, so I'm not going to do all the calculus right now. Although again, if you have questions on it, just let me know, I can go through it. But we would take each of these derivatives. So we would take the derivative of this by doing like the two downwards, and then multiply that by the constant and do the chain rule, and then same thing with this one, and then same thing with that one, and then multiply all of those derivatives, and it gives us the one big derivative. And we'll essentially just keep doing that for the rest of these models. And one nice thing about this, which we, I guess, don't necessarily have time to go a whole lot of detail into, is that once you get to this point, the derivative up to this specific point, d2, is going to be shared by all of the things here. So if I wanted to update u10 and u00, they're connected to d2, so the error that I found up to that point, the derivative, applies to everything to the left of it in the backpropagation section as well, right? So we can kind of reuse things, and that's kind of how we can make this a little bit more efficient. And eventually, we would work our way back and do the derivatives until we hit all of these things. So finally, by taking all those derivatives, applying it to that, what was it called? Gradient descent that we did earlier, then we can update all of these so that they are now slightly closer to minimizing the error, and therefore slightly closer to doing a better job predicting the thing. And so just we'll end on this, is just the last process you would do is you would go through all of those inputs we talked about, compare each of them, plug in all the stuff, and then eventually, if you do this enough times, it should update itself to a point where the error is relatively low and your model does a pretty good job with predictions. And it's kind of the goal with machine learning in general, is you just want to iterate until you train it in such a way that it's good at predicting things. And so that's our foundations for machine learning. And if you want to look up more about this, or look up the derivatives yourself, or do any of the calculus, then this specific example is an artificial neural network. And we did it for a regression here. I didn't have time to talk about the difference between a regression and a classification, but this was a regression, and that's what that is. So I don't know if we'll talk about this more after the test, but there's at least an intro to machine learning and neural nets. If you have any questions, feel free to stick around and ask me something. Just a reminder that the exam is again on Tuesday, so normal class time, probably be some extra time. I think it doesn't cover linked lists anymore, so it's a little bit shorter, and we won't have class until the next Tuesday after that. I think the 16th we said. Okay, so best of luck on the test. If anybody has any questions, just let me know. And yeah, I'll see you guys in 2 weeks.